In order to describe wave, there are different wave theories available. But what we want to highlight here is that the wave that we see in the coastal area, they have different amplitudes and different periods, and usually superimpose with one another, so that it becomes highly varied and irregular. And they are also transient. That means they changes all the time, and that's why it is highly complicated. So to describe this complex observation, different wave theories has been introduced by different researchers. We have Airy wave theory, which is also known as a small amplitude wave theory. This will be the primary wave theory that we are going to discuss in further detail later. But there are also other wave theories such as trochoidal wave theory, Stokes finite amplitude wave theory, the KdV noidal wave theory, solitary wave theory, and nonlinear wave theory. Each and every types of wave theories here differs, and it is beyond the scope of our present lecture. These are examples of the different nonlinear wave profile. What we see here is example of Stokes waves, whereby as you observe there is a sharp peak. We have an example of a noidal wave, whereby the trough is much longer compared to the crest, and we have example of a solitary wave. So the different wave theories try to be able to describe this surface profile and the propagation of these different waves. Meanwhile, the small amplitude linear wave theory by Airy is the simplest, and so is frequently adopted for practical application. He described the wave profile as a sinusoidal form, and so it is of course limited in its practical application, and so the results obtained typically must be treated and interpreted carefully. Here we have a long list of the assumptions of the linear wave theory. It assumes that the water is homogeneous and compressible with negligible surface tension, and Coriolis effect also can be neglected. So that means there's no internal wave and there's no pressure wave effect. Also, flow is rotational and the fluid is ideal, such that potential wave theory can be applied, and there's no shear stress on the AC interface. Also, the boundary at the bottom is a slip boundary condition. We assume that the seabed is fixed, impermeable, and horizontal, so that when the wave propagates over the seabed, it doesn't add or remove any energy from the flow. Pressure on the AC interface is assumed to be constant, so that hydrostatic pressure difference due to the surface changes is negligible. The waveform is invariant, it doesn't change with time or with space, and the waves are plane or long crested, so that it is two-dimensional. Last but not least, the wave amplitude is small compared to the wavelength, and also the wave amplitude is small compared to the water depth, and that means water particle velocity are small compared to the wave celerity, so that the wave theory is applicable only to shallow water and near breaking waves. To summarize it all, the linear wave theory is applicable to a two-dimensional freely propagating wave with low steepness. We'll define this in more detail later on. Now this may sound like a long list, but don't worry, we will emphasize some of the point as we go along when we discuss the linear wave theory. This plot here shows the distribution of the different types of wave in the sea. We have the normalized water depth here, represented by the D, and we have the normalized wave height here, represented by the H. So as we go in this direction, is larger depth, here is smaller depth, and as we move in this direction is larger wave height, and as we move down is the smaller wave height. So for different depth and different wave height, we have different category of wave. Notice here that for large water depth we have deep water, small water depth we have shallow water, and in between we have the transition water. And at this different region, depending on the height of the wave, if the wave height is very large, it tends to be breaking wave. If the wave height is small, it tends to be non-breaking wave. And so in these different regions, the surface wave profile changes so that different wave theory may best describe the wave. For example, Stokes fourth order theory will be the best to describe wave in this region, or Stokes third order in this region, Stokes second order in this region, Noether wave in this region. The linear wave theory is good to be used to describe wave in this region, mainly in the deep water and in the transitional water region, whereby the wave height is not too large. So that is the region that the linear wave theory, which we will discuss in more detail, that's where it is applicable. So if the condition is outside this region, then we need to be aware that linear wave theory is no longer directly applicable, and so we may have to use more sophisticated nonlinear wave theory.